Welcome, welcome, welcome. Let's just go down the line. Can you briefly give us your name? And again, briefly, just like the Space Tech panel, I mean, we've got a lot to talk about. So briefly, what you and your company do. Sabrina.
Yes, my company, Algorithmiq, develops quantum algorithms and software for the life sciences, so specifically to discover and develop new drugs by using the power of quantum computers.
So quantum drugs.
Well, I wouldn't call them so, but yes, I mean.
All right, fair enough, fair enough. Markus?
Yeah, Terra is a quantum as a service company. So the majority of what we do is hardware agnostic quantum software, tackling use cases across industries. And another big pillar is quantum security.
Good, good. I want to get into that later. And Jan?
I represent IQM quantum computers. So what we do is we build the computers, so the actual hardware and systems, based on a superconducting technology. There's still a few technologies out there, so we have chosen this one. I think what makes us special is that on the one hand side, we focus a lot on so-called HPC integration, so bringing those systems into high-performance computing centers. And then also what we do a lot is building ASICs, so specifically designed processors for certain algorithms.
Okay, so we've got the builder, the servicer, and the algorithm maker. I feel like that's the baker, the candlestick maker, kind of, right. Well, that's a whole other conversation. You know, we've all heard the axiom, software is easy, hardware is hard. Tell me about the challenges the quantum computing industry is facing. Markus, talk to me about, you know, hardware is hard, quantum is...
Well, yeah, I mean, I think the challenges are, in a way, quite typical as for other deep tech disciplines, right? They are really frontier tech disciplines, so it needs a lot of education and upskilling of all stakeholder groups, from investors to target clients. And of course, it is products in development, right? And for quantum, it means we have to develop the whole compute stack from scratch, hardware, software. And you know, that's where the different players kind of are segmented. One focus on software, one on hardware. Definitely the hardware challenge is the biggest one. We have to get scalable quantum chips without too many errors so that we can use them beyond just for toy problems. And I think that's the major challenge in the industry.
And Sabrina, correct me if I'm wrong, this is exactly what you're working on, is making things better and easier.
Yes, but rather than focusing on really the engineering at the hardware level, we are focusing on what we can do with existing and evolving quantum computers by using smart, noise-resilient algorithms, which means facing upfront and immediately one of the major challenges of quantum computers, that is the fact that they are so sensitive to noise and to errors that they need to be protected against this imperfection, and this can be done at software level. This is what we are doing, integrating them with high-performance computers. So building algorithms that are both quantum and classical at the same time.
Okay, all right. And Jan, I mean, what is IC? I keep saying ICQ. Every time I see it, I want to say ICQ. IQM, what are you doing to maybe put Sabrina out of business? I mean, can we make quantum computers even better?
Well, of course, we can make them better. We must make them better because at the moment they're not working well enough. It's a kind of a chicken and egg problem because, of course, we would like to see a market pull from the industry that they are trying out applications and use cases. And but then the industry says, well, but the machines are not working yet, right? So it's kind of who makes the next investment first. But I think it is anyway so that we will see developments both on the algorithm side and on the hardware side. And the question is kind of when do those lines cross? In this sense, I think there is a very clear development path. So many companies have published roadmaps, so you can see actually what are the next steps. And in this sense, I'm actually very confident that we will see still a lot of improvement. And also the more we pull in industry from the side, so not quantum experts, but people who kind of help developing the stacks, computer scientists, semiconductor experts, we will see an acceleration actually of the process.
Good. In preparing for this panel, I watched a lot of YouTube videos. I feel like I could be a member of your staff by now. I know all about, well, I know of quite a few bits about qubits and one state and another state. But having conversations with friends and family, one topic that kept coming up, and I think it is quite relevant, and also for our audience as well, is at the end of the day, what does quantum, like how does quantum computing affect me in my day-to-day basis? You know, I'm just trying to go about my business as you are, but what does quantum computing hold, you know, for the future? I know that I realize that's a huge question. Markus, go for it.
Well, look, I mean, the underlying technology shows an exponential increase in compute power. I think this says a lot. Everything is more or less outperformed sooner or later by the exponential function. So everything which has to do with big data analytics in optimization, simulation, machine learning is getting sooner or later disrupted. And that means stuff like your individual security, the security of your data is affected, as well as, and that is probably the thing which you care most, you know, about your loved ones, personal health. I think health, life science will be massively affected. I'm just opening it up for you. But, you know, drug simulation. I mean, the drug discovery today is more or less the ability to simulate on a high-performance computer. That will be, you know, transformed into quantum simulations on a quantum computer, and that will open up the door for a lot of great things.
Sabrina, take it.
Yes, of course, and I can only confirm. I have to say, to add and to take it from perhaps a slightly different perspective, is that quantum technology clearly is a real disruptive technology. So it's impossible to say, you know, in some sense, the main message is that it will affect everyday lives and everyone's lives. So think about the life without and with the internet. I mean, internet has been one of the technologies which has changed our society. And similarly, it is impossible to think of a, if you want, of a field of our society that will not be affected by, you know, computing power that changes substantially. Which is not to say that quantum computers will be able to outperform conventional computers in everything. This is not the case, but the quantum boost provided by quantum computers will affect basically almost every sector.
And this has been, you know, like the promise of quantum computing has been theoretical for years, right? And I'm all for these benefits that you just outlined. Markus, I found a tweet of yours, and this is why Twitter is such an ugly beast, because the internet is forever.
Everything is archived.
The internet is forever. In 2021, you said, we're not talking 10 years, it will be within 2 to 5 years, or these promises will be available in 2 to 5 years. How are we doing on this prediction so far? That was 3 years ago.
Yeah. I would keep up to that.
I think, all right, so you got 2 more years left on this prediction.
No. Well, if you count it kind of conservative, it's actually we are here, right? 2 years plus. So, and I think we are. You know, the thing is, we are not yet there on the quantum hardware. Not yet scalable enough. Not yet really suitable to deal beyond toy problems. But the hybrid approach, mixing the best of breed of classical high-performance computing, early available native quantum chips, this putting together in a hybrid approach, especially simulating qubits to create the hardware underground to run our quantum software on it today, that creates already, if we select the use cases wisely, an outperformance vis-a-vis best-in-class classical supercomputing implementations. And I could give you a lot of examples where we work on. We don't have the time for that, but in optimization, simulation, great cases where we have substantial business performance enhancement via the hybrid approach. Short answer, I think we delivered. We are there with the hybrid approach. And we have 3 more years, right, to deliver on the hardware, at least to get more meaningful chips.
Jan, are we going to make it in 3 years?
Well, it's not that black and white. It's not so that suddenly there's like a
it's a 1 and a 0,
computer,
you might say.
Yeah, that does everything. But I mean, what we have seen already on several platforms is that quantum processors have been outperforming big supercomputers. The issue is there was no kind of commercial application or so behind this. It was like a mathematical problem. But you see, the power is already at the edge. And so what we believe is what's going to happen is that it comes algorithm by algorithm in a sense. And of course it starts, this is very natural, by simulating quantum physics, because this is what quantum processors are naturally good at. And then you might ask, okay, but is this a commercial use case or not? But then if you talk to big, probably pharma or chemistry companies actually, which have big R&D units, they're already working on those today. Of course, they don't use them in their products, but they might be in their products in a few years. So I think we will see this gradual kind of entering of quantum into the market, and I don't think you can say, wow, now on day whatever, May 25th, suddenly it worked and before not, but we are actually very well on track, I think, to in these timelines to get the first algorithms run on quantum systems, which cannot be done anymore on classical computers.
Sabrina, we've got a hybrid approach here, we've got a pure quantum approach. I mean, do you envision a time where your offer is I want to say not even an afterthought, but it's just built into a quantum system? So in other words, the noise resilience won't even be a thing anymore, it will just be.
Yes, of course, we do know that in the future we will have, in a timeline that could be 10 years or so, we will have computers that work according to the same principle of error correction of existing computers. And again, the transition towards error correction will be gradual and will clearly need improvements that are more related to engineering and chip manufacturing, but at the same time we'll also need development from the perspective of algorithms and codes that allow for what is known as fault-tolerant quantum computation. So quantum computation which is protected by definition by errors. And this is the moment in which we will have the full disruptive exponential power of quantum computers. But before that, there will be already commercial applications that will come from the existing quantum computers that are not yet error corrected, but that through error mitigation techniques are able to outperform really classical conventional methods. So it will be an exciting moment, the moment in which this transition will happen, and we will see the applications grow both in number and also in power.
Okay, all right, good. One last question, because we are running short on time. I told you this was going to go by very quickly. It's a huge topic in 20 minutes. Earlier this month, we all saw the piece that the FT published, right? About the Q date, right? I mean, it was one of the most beautiful, if you haven't seen it, go read it. One of the most beautiful and simplistic distilled down versions of what quantum computing can do. Is it really fear-mongering, this Q day? I mean, is this something that we really need to be concerned about? You know, quantum computers being able to basically destroy every layer of security that we have. And if so, what can we in Europe do to take advantage of this situation? And I don't mean breaking into people's bank accounts. I mean providing, well, you know what I mean. Go on. Jan, what do you think?
So generally there are quantum secure algorithms. So what everyone just needs to do, and this sounds simple, is to change the encryption code. But of course this means the whole community has to agree on what is the new one. The real danger in my eyes is this concept which is called store now, decrypt later. So if you would have bad thoughts and you just store now all the data that you collect, and you think maybe still in 10 years there is some relevant information in there which is dangerous to people, and in 10 years we have a fault-tolerant quantum computer, then this can be used against certain things. But at the moment what needs to be done, and people are working on this, is a change of the encryption system. Okay,
okay. Does that resonate?
Absolutely.
I mean, that's what we do, right? I mean, let's spin it in a positive way. Yeah, we do have the quantum threat. We learn more or less every month that the threat comes nearer, that we potentially need lower number of qubits to decipher, regardless of symmetric or asymmetric classical encryption. So we have to upgrade to a quantum secure standard now, also because of that concept, but we can do it. So we are working on QKD protocols, and the great thing, the positive spin is, a once quantum encrypted communication protocol will never ever be hacked again as long as the laws of physics in this universe don't change. That means this is the final end game on cybersecurity. Once you upgrade it to a quantum secure level, you are safe, and we can do that, and we'll do that. So I think it's a positive thing. It's it's a great transformation.
So you're telling me I never have to install any antivirus ever again? Fantastic, fantastic. Listen, we are running short on time. We could talk about this for another 2 hours, I think. But ladies and gentlemen, quantum computing.